All right, next we have Matthew, and he's going to tell us about how to implement these Lindbladians.
All right, so I guess people can hear me in the back, hopefully. So just wanted to quickly thank the conference organizers for giving me a chance to talk about some work I did with my supervisors, Devira and Nathan. So just an overview of the talk. Well, I guess a perk of going in the afternoon is that a lot of things were motivated very nicely for me already. Everybody else did a great job. So yeah, I'll briefly review what at least I mean by Hamiltonian simulation. I know at this conference a lot of people mean different things. There's analog, there's experiment, there's numerics going on. So I'll also briefly motivate Lindbladians, which was, again, already done quite nicely today. And then I'm going to talk about this approximate correspondence between Lindbladian equations and these things called repeated interactions, which are these completely positive and trace-preserving maps. And it's another way to do open system dynamics. And then we're going to use these maps that I discussed to formulate some iterative unitary process that will converge to these dynamics. And this will allow us to implement this on our computer. So there was a question asked earlier of what's your favorite Lindbladian simulation algorithm? It might seem that that's the question I'm going to answer today, but you could also argue that through doing this mapping, I'm avoiding the question entirely. Okay, so briefly, we know states are evolved by the unitary propagator. I'm talking about digital simulation here. So we're going to implement some unitary that's going to approximate this propagator within some p-norm or epsilon. And motivation, yeah, we can study the time evolution of certain observables or quantities of interest, or learn the eigenvalues. And similarly, with the dissipative dynamics, we can study the time dynamics of these dissipative observables. Yep. Oh, yeah, sure. Still on? Yeah, sounds good. Okay, sorry about that. Yeah, so this has been motivated for me nicely already. The algorithmic question I'm interested in is how to efficiently build this unitary. And just for reference later in the talk, some state-of-the-art results come from Qtization or the quantum singular value transformation, where we have a linear t-scaling multiplied by a coefficient norm. When you write the Hamiltonian as a linear combination of unitaries, that's what that alpha is. If you're not familiar, you can think of it as like the energy scale of the problem, plus some polylogarithmic function in the error. Okay, and now just briefly, Lindbladians. So this is also a CPTP generator, and it's going to describe the dynamics of a system coupled to an environment. And this gives an accurate description of Markovian dynamics. And what that means is, in the context of open systems, we don't need any notion of history, because in Lindbladian dynamics, there's no correlations built up between the bath and the system itself. So we've already seen this equation a couple times, where here the L's are these jump operators, which are derived usually from interaction Hamiltonian, or they can also be chosen for a model, depending on if you're going for a physical derivation or not. And then we have these gammas, which is the rate at which this dissipation happens. So I can pull up a laser, sure. And then this is solved similarly with an exponential, like in Hamiltonian evolution. However, here we're using this L as a super operator. If you haven't seen these things before, you can think of this as this defined via its Taylor series, where if you have the square of a super operator that's a commutator, you're just applying that commutator twice. An important fact is that this is a quantum channel for all positive time. This is also what makes it difficult to come up with algorithms for Lindbladian simulation, because the higher order Trotter formulas need negative time, and then we no longer have a CPTP and don't have the nice properties of our density matrix. And this reduces to Hamiltonian the von Neumann equation when all these jumps are zero, of course. All right, so now on to these repeated interactions that I'm interested in. These are also Markovian dynamics, and it's generated by these repeated sort of short time Hamiltonian evolutions with traceout. And you can think about embedding these non-unitary dynamics of Lindblad into a larger space via Steinspring dilations. So just to talk about our spaces here, our total Hilbert space will be that of the Hamiltonian tensored on with the environment, where for the purpose of repeated interactions, we'll construct the environment as many small environment subsystems. And we'll have a Hamiltonian that looks like this, where we have our free Hamiltonian that acts on our system that we're interested in, as well as the environment or the bath that's evolving under its own Hamiltonian, plus some interaction. And we can control how many of little discrete pieces of the bath we have. So for some short interaction time, again, it looks quite like a science-based dilation here, because it is. The action of the map is to tensor on a piece of the environment, perform this joint evolution under the total Hamiltonian, and then trace out over this environment that you tensor on. And then by iterating this map over and over again, we can generate these Markovian dynamics for an evolution time t. So just to iterate kind of how the map is going on, to make everything concrete. For references up there, we have our system, an environment. The first action is to tensor on a piece of this environment. Then we're going to perform a joint unitary evolution under some interaction Hamiltonian. Then we're going to trace out or discard this evolution, and at the same time, turn off this Hamiltonian. And then it's ready to start all over again with the next piece of the bath. And then you just chug through this, and we can show that under certain conditions, you can converge to Lindbladian dynamics in this way. And just for some cleaner notation, we can use a super operator. And I'm just using this tilde here so I don't have to write out that entire Hamiltonian I had from before. But writing it as a super operator, we can use a nice property to just write the map in a cleaner form like this, which is useful for analysis later. And just to give a physical intuition for like systems that might evolve like this actually in nature, a system that sort of is analogous to repeated interactions or these collisional models is that of like a maser. So if you think of like a cavity that you want to describe the dynamics of, and maybe it's perturbed iteratively with, let's say, atoms or like ions coming out of a furnace, this is a way that they would like strongly couple for very short times, but you'd get dissipative dynamics in this way. Okay, so now what I want to show is that there's a approximate correspondence that exists between these two approaches. So if we place a constraint on the interaction strength for the Hamiltonian I had on the slide before, such that the coupling is 1 over root of the interaction time, you can show just through an exercise of Taylor expansions of superoperators that this converges to Lindblad dynamics. I don't have much physical intuition to give to you for why this is the limit. It just goes through. And interestingly enough, a similar limit also allows you to converge from stochastic Schrodinger equations to Lindblad dynamics in a kind of another regime that's investigated in a work that came out around the same time. So also encourage looking into that if you're interested. So I'll just give an informal statement of the theorem here, just to give an idea of how it works. So if we use this limit above that I talked about, as well as you compose the map in a very particular way, so we have like M sort of compositions, it's like M composed of all of the different interactions, which set out to model each different possible jump operator you can have in the actual Lindblad equation. Again, under the limit, you can show the following bound. So this is just an induced norm over density matrix. That's what this weird one-to-one look means. And we're just bounding the exact evolution from the Lindblad dynamics and taking the difference with our map. And we see that we get some t-squared evolution. And this new is sort of this iteration parameter that we're iterating this M-composed map new times to control the error. So if you set this equal to epsilon and we arrange for new, then we get a scaling on how often, like what our number of iterations has to look like. And yeah, like I said, it's t-squared multiplied with the Lindblad norm, and then some conditions on this gamma being the largest interaction of the, large eigenvalue of the interaction Hamiltonian, but the tighter part of the bound is the leading term. All right, so we can now construct using this repeated trace-out dynamics to converge to Lindblad. So I can give some nice quantum circuits. So if we have all of our environment and Scylla prepared, you can just do these joint unitary evolutions with our system registered at the top to converge to approximately the Lindblad evolution. And if we prepare our ancilla as single qubit thermal states, we can efficiently prepare them as well and derive our jumps sort of from that interaction with them. You could also make this much more space efficient by iteratively tracing out, but I write in both cases, since if you want to, let's say, implement U in some way that's not deterministic, that you want to do amplitude amplification at the end, this keeps the entire process unitary until the end. But if not, like if we're using Trotter or something, we can just implement, trace out, and prepare our path on the fly. And now, the advantage of doing this is that we can use state-of-the-art Hamiltonian simulation algorithms to prepare these unitaries. Okay, so now in terms of the complexity of the whole algorithm, we also investigate Trotter in the work, but the best scaling comes from computerization, so that's what I'll talk about here. So we need to construct, prepare and select oracles that have been discussed earlier today in order to get our sort of like LCU block encoding. So we write the total Hamiltonian like this, which is sum of the free, environment, and interaction Hamiltonian again. And this tau just means that I've absorbed that coupling of the 1 over root tau in here, because in qubitization I can just treat like time as a parameter. And then this is our sort of total Hamiltonian for each interaction, where alpha are coefficients and a's are unitaries. So, like I said before, we have a prepare oracle, which acts on an ancilla register to encode all of these coefficients for our unitary decomposition. And then a select one, which, using some control logic, sees the ancilla register state and applies the correct unitary to our state of interest. And just to show you how these act together, you can prepare this block encoded Hamiltonian like so. Now, the art of qubitization requires we construct a walk operator that involves 2 queries to prepare and 1 to select. So asymptotically, it's the same amount of queries to each. So informally, I'll state another theorem that says, well, using qubitization, we can have these QPS queries that scale like so, where it looks like there's a lot going on here, but well, taking a max for the worst case of all the interactions, we have the coefficient norm for the free Hamiltonian. We have m being the number of ancilla multiplying by the bath frequency, because in this case, again, I was talking about single qubit ancilla states. And then we have the coefficient norm for the interaction and some root t nu, or if you recall, nu was the amount of times we need to apply the repeated interaction map to control the error from the Lindblad dynamics. And then we have this sort of polylog of 1 over epsilon factor that comes in from qubitization that we saw earlier. So now if we consider the case where we're weakly coupled to our bath, or where the coefficient norm of the interaction Hamiltonian is small, it starts to look a lot like the state-of-the-art results that I showed for Hamiltonian simulation on the first slide. But the point of this isn't to say that this achieves that for Lindblad simulation. It doesn't, because that would be when nu is treated as a constant, but in reality is not. We do have to converge to the Lindblad map in the first place, so really this goes like t squared here. I more so state this because it raises an interesting further question for open system dynamic simulation. And that is which method, like Lindblad simulation, like Lindblad equations or repeated interactions, actually captures the more accurate physics. So I'm talking about like a model error here. Like if you think about the system I said before of the maser might already be described quite nicely by the repeated interaction map that we can efficiently implement, and maybe that nu actually does behave as a constant in that case, whereas maybe another system like a Heisenberg model where you're doing creation annihilation operators on as your sort of jumps might not be as well captured, in which case nu might not scale as nicely. So it's interesting because we're converging to something that is already an approximation in the coupling, which is the Lindblad master equation. And just quickly, some other things. Can these repeat interaction style maps generate higher order convergences? If so, probably new techniques would need to be used to analyze these, as if you've ever tried to Taylor expand a Lindblad evolution beyond second order, it's a nightmare. And also, can the complexity of the optimal Hamiltonian simulation be achieved for Lindblads as well. And for some state-of-the-art results for Lindblad simulation, see these papers I listed. These achieve scaling like t, polylog t over epsilon, I believe. Also, there's a lack of numerical studies in these schemes to see how, when you actually implement these, how the resources truly scale. And to do other, like better maybe unitary approximations exist towards Lindblad simulation on a quantum computer is also something I'm interested in. Yeah, that's everything. Thank you for listening.
Right, any questions?
Are there any situations where this repeated interaction to Lindblad map can be reversed? So given some Lindbladian, do you know how hard is it to find some repeated interaction that implements it?
Okay, yeah, that's a great question. I think that's the main struggle with this approach is it's easy to say, okay, I have this like interaction Hamiltonian, we can derive jump operators from that. So if you're, in terms of physical derivations, it's easy to get the repeat interaction map. To go the other way, where I say I have a very efficient repeat interaction map, let me see how. Yeah, it's very difficult to go the other way, and I don't have a good answer of how one would go about doing that. Thanks for the question.
You can. Thanks a lot for the talk. Sorry, I want to clarify, is there any limitations on the locality of the jump operators which come from the locality of Hamiltonian, or essentially, can you simulate non-local Lindbladians in this way?
So there are, in writing the map this way, some sufficiency criteria to be able to actually do this. I'm not sure that there are restrictions on locality. So, for example, when you write down the repeated interaction map, the interactions that actually act on the system can be general. In terms of the interactions that act on the bath, there would be some criteria there. Locality. It'd be interesting to work locality into this picture. It's not something I've really considered. Yeah, it's a good question. Happy to discuss more of it later. Thank you.
Thanks.
Any more questions? If not, let's thank Matthew again.